A machine is supposed to fill packets with 500 grams of flour. You weigh a sample, and the average comes out at 505 grams. So, is the machine genuinely overfilling? Or is this just the luck of the draw? Hypothesis testing is how we answer questions exactly like this. The idea is almost a courtroom. We start by assuming a default claim is true. We measure how far our data stray from it. And then we decide, is that gap small enough to shrug off as chance, or so large that we can't believe the default anymore? We'll build the whole machinery step by step and put it to work with a z-test and a chi-squared test from start to finish. Let's begin with the two claims at the heart of every test. Every test begins with two rival statements. The first is the null hypothesis, written H0. It's the default, the boring claim of no effect. Here, that the true mean really is 500 grams. We give it the benefit of the doubt, exactly like a defendant is presumed innocent. The second is the alternative hypothesis, H1. It's what we suspect instead, that the mean is not 500. The whole test is a contest between these two, and the data are the only witness. The alternative comes in three flavors, and choosing the right one matters. If you only care whether the mean went up, it's red-tailed, mu greater than the target. If only down, left-tailed. And if any change at all counts, up or down, it's two-tailed, mu not equal. Now, how do we measure the gap between the data and the null claim? Not in raw grams. A 5-gram gap means one thing for a precise machine and something else for a sloppy one. We measure it in standard errors. A quick but crucial distinction. Sigma is the spread of individual measurements. The standard error, sigma over root n, is the spread of the sample mean, and it shrinks as your sample grows. Bigger samples give steadier averages. The test statistic is simply that gap, counted in standard errors. Take the sample mean, subtract what the null predicts, and divide by the standard error. This is the z-statistic. It answers, in one number, how many standard errors the data sit away from the null. Here's the beautiful part. If the null is true, the z-statistic doesn't just wander anywhere. It follows a known curve, the standard normal bell, centered at 0. Small z values, near the middle, are exactly what we'd expect by chance. But way out in the tails, far from 0, a z value would be a genuine surprise if the null were true. So we mark off those extremes as the rejection region. For a two-tailed test at 5%, the cutoffs are at plus and minus 1.96. The total tail area we set aside is the significance level, alpha. Here, 5%. It's the risk we're willing to take of raising a false alarm. And the decision rule could not be simpler. If the statistic lands in a red tail, we reject the null. Otherwise, we don't. There's a second, equivalent way to decide. And it's the one you'll see most often. The p-value. Suppose our test statistic comes out at z equals 2. Mark it on the bell. The p-value is the shaded tail area beyond that observed statistic. The probability of seeing a result at least this extreme, purely by chance, if the null were true. For a right-tailed test, that's the whole tail to the right of 2. Plug in the numbers. Phi of 2 is 0.9772. So the p-value is 1 minus that, about 0.023. A small p means the data would be surprising under the null. And here is the decision rule in its cleanest form. Compare the p-value to alpha. If p is smaller than alpha, the result is too extreme to be chance. We reject the null. If p is at least alpha, we do not reject. Our p was 0.023, below 0.05, so we reject. No test is perfect. The data can fool us in two opposite ways, and it's worth meeting both. A type 1 error is a false alarm. We reject a null that was actually true. Its probability is exactly alpha. The significance level we chose, a type 2 error, is the opposite blunder. We fail to reject a null that was actually false. A real effect slips past us. Its probability is called beta, and 1 minus beta is the power of the test, the chance of correctly catching a true effect. Picture both worlds at once. The blue bell is the world where the null is true. The green bell is the world where the alternative is true. The same statistic, just shifted. Our cutoff line sits between them. The blue tail past the line, shaded red, is alpha, the chance of a false alarm when the null is true. The green area on the near side of the line, shaded rose, is beta, the chance of missing a real effect. Push the line to shrink one, and the other grows. That trade-off is the quiet tension inside every test. Let's pin down when each test applies, starting with the z-test for a mean. Use it when the population standard deviation sigma is known, or when the sample is large enough that the sample deviation S is a trustworthy stand-in. Under the null, the statistic follows the standard normal. But what if sigma is unknown and the sample is small? Then we estimate the spread from the data itself using S and switch to the t-statistic. It looks identical with S in place of sigma, but it follows the student t-distribution with n-1 degrees of freedom. The t-curve has slightly heavier tails than the normal. It's more cautious with little data. But as the sample grows, it settles down and becomes the standard normal. So the rule of thumb is short. Sigma known or big sample, use Z. Sigma unknown and small sample, use T. Now the full ritual, back to our flour machine. The population deviation sigma is 4 grams. We weighed 36 packets. The sample mean is 505, and we'll test at the 5% level. Step 1. The hypotheses. The null is that the mean is 500. We want to catch a change in either direction, so the alternative is two-tailed. Mu not equal to 500. Step 2. The statistic. Sigma is known, and n is a healthy 36, so it's a z-test. The standard error is 4 over the square root of 36. 4 over 6, which is 2/3, about 0.67 grams. Now the z-statistic. Sample mean minus the null value is 505 minus 500, which is 5. Divide by the standard error, 2/3. That's 5 times 3 over 2, giving z equals 7.5. The data sits 7.5 standard errors above the target. Step 3. The critical values. A two-tailed test at 5% puts the cutoffs at plus and minus 1.96. Anything beyond those is the rejection region. Step 4. The decision. Our Z is 7.5, far out in the right tail, deep inside the rejection region. So we reject the null hypothesis at the 5% level and always finish in plain words. There is strong evidence that the true mean packet weight is no longer 500 grams. The machine's average fill really has drifted, and here it drifted upward. Means aren't the only thing we test. The chi-squared test handles categorical data, counts in categories. It compares the counts you actually observed with the counts you'd expect if the null were true. Using this sum, observed minus expected, squared, over expected. Here's a concrete question. We survey 160 people about their drink, tea or coffee, and their age group. Are age and drink preference independent or linked? These are the counts we observed. Step 1. The hypotheses. The null says age and drink preference are independent. Knowing one tells you nothing about the other. The alternative says they're linked. Step 2. The expected counts. If the two were independent, each cell's expected count is its row total times its column total, divided by the grand total. Every row and column here totals 80. So each expected count is 80 times 80 over 160, which is 40. All 4 cells expect 40. Step 3. The statistic. Every observed count is either 50 or 30, and every expected count is 40. So each cell contributes 10 squared over 40, which is 100 Over 40, 2.5. 4 cells, each 2.5. Add them up, and the chi-squared statistic is 2.5. 4 times over. A total of 10. Step 4. Degrees of freedom and the decision. For a table with our rows and C columns, the degrees of freedom are our -1 times C minus 1. 2 rows, 2 columns, gives 1 times 1. Just 1 degree of freedom. For 1 degree of freedom at 5%, the critical value is about 3.84. Our statistic, 10, sails well past it, so we reject the null. In plain words, age group and drink preference are not independent. They're genuinely associated. Your turn. A process should run at a mean of 100. Sigma is 15, you take 25 samples, and the mean comes out at 106. Test at 5% whether the mean has risen above 100, a right-tailed test. Pause here and work it through before I do. Here's the walkthrough. The standard error is 15 over the root of 25. 15 over 5, which is 3. Then Z is 106 minus 100 over 3. That's 6 over 3. So Z equals 2. Because it's red-tailed, the p-value is the tail beyond Z equals 2. 1 minus phi of 2, which is 1 minus 0.9772. So 0.023. That's below 0.05. So we reject the null. The mean has significantly increased. If you got that, you've truly got this. Trap 1. And the most important. Failing to reject the null does not prove it's true. It only means the data gave no strong evidence against it. We never say we accept the null, only that we fail to reject it. Trap 2. The denominator. The test statistic always divides by the standard error, sigma over root n, never by sigma alone. Confuse the spread of individuals with the spread of the mean, and every z comes out wrong. Trap 3. The wrong test. When sigma is unknown and the sample is small, you must use the t-test with s and n minus 1 degrees of freedom, not the z-test. Reaching for z there quietly overstates your confidence. Trap 4. Chi-squared degrees of freedom. For a contingency table, it's rows -1 times columns -1, not n minus 1. Getting the degrees of freedom wrong sends you to the wrong critical value entirely. And trap 5. Ignoring assumptions. The Z and T tests lean on approximate normality, and chi-squared needs expected counts that aren't too tiny, around 5 or more. Skip the checks, and the conclusion may rest on sand. Let's lock it all in. Every test starts the same way. Write the null and the alternative, and pick your significance level alpha. Then compute a test statistic that measures the gap in standard errors. A Z or a T for means, a chi-squared for categorical counts. Finally, decide. If the p-value is below alpha, or the statistic falls in the rejection region, reject the null. Otherwise, don't. State the verdict in plain words. And remember, we test the null. We never prove it. Do that, and no hypothesis test can catch you off guard.